So in this video we are going to state and prove Taylor's theorem in full analytical rigour. Now I have another video on Taylor's theorem that is in the calculus playlist. In that video we also prove the theorem, but we do it more from a calculus angle than an analysis angle. So we didn't worry about the full analytical technicalities of exactly what the minimal requirements are in order to be able to apply Taylor's theorem. In this video we are going to worry about those technicalities. However, the basic proof argument that we use in this video is going to be the same proof argument that we use in that video, i.e. it's going to use repeatedly Rolle's theorem. So Rolle's theorem is a prerequisite to this video. I have a previous video in the playlist on real analysis on Rolle's theorem where we prove Rolle's theorem. So if you're not familiar with that theorem, please do watch that before watching this. The other thing that we're not going to do in this video that we did do in the video on the calculus playlist is we're not going to look at the application of Taylor's theorem. So we're not going to look at using it to prove that infinite Taylor expansions actually do converge to their functions. If that's something you want to see, please do watch the videos in the calculus playlist. So let's begin with the setup then. So we're going to have some function that we'll call f that is going to be defined on the closed interval from a to b, so a subset of the real line, and it's going to be a real valued function. And Taylor's theorem is going to use a natural number, so we'll call this natural number little n. It could be a small natural number like 10, for example, or it could be a very large natural number like a million. In which case you'll have to do a lot of differentiation, but it doesn't matter. Taylor's theorem is going to apply for all of the natural numbers. So we have our general natural number little n, and given that natural number, we're now going to require that our function be n times differentiable everywhere on the closed interval from a to b. So we're going to demand that the first derivative, the second derivative, all the way up to the nth derivative, they're going to exist on the closed interval, and they're going to be continuous, actually, on the closed interval, or they're going to need to be continuous on the closed interval. Are continuous on closed interval from a to b. In order for us to be able to apply Taylor's theorem, this is one of the criteria that needs to be true. So let's just have a look at this in a little bit more detail. So we'll start with the first derivative. So the first derivative existing even everywhere on the closed interval a to b means that this function f is going to have to be differentiable everywhere on the closed interval from a to b. Differentiability implies continuity, so immediately we know that f is going to have to be continuous everywhere on the closed interval from a to b. Now you can then view the first derivative f prime as being a function itself on this closed interval from a to b, and it's going to be a real valued function. And the way it will work is it will just carry any point in this interval to the value of the derivative of the first function. So we know it's differentiable everywhere on this closed interval. So any point x inside here will have a derivative, and this is then just going to map that point onto that value. For it to then have a second derivative means that this function, the first derivative, is going to itself be differentiable everywhere on the closed interval from a to b. And the value then of that derivative of the first derivative is then going to be the second derivative of the function at any point. So the second derivative will then be a function itself from the closed interval ab into the real line. And we're insisting that this is going to carry on n times, so n times this function is going to be differentiable everywhere on this closed interval from a to b, and we want these functions, the first derivative, the second derivative, all the way up to the nth derivative, to be continuous everywhere on this closed interval from a to b. Now that is given to us for free for all of the derivatives apart from the nth derivative. So the first derivative is guaranteed to be continuous everywhere on the closed interval from a to b because it's going to have to be differentiable itself everywhere on that closed interval in order for you to then have the second derivative everywhere. So because it's differentiable, continuity is then implied for this one. And the same for the second derivative, because the third derivative is going to exist everywhere on the closed interval from a to b, that implies that the second derivative must be continuous everywhere on that closed interval. this goes on all the way up to the n plus 1th derivative that will be kind of here. It's going to be ensured to be continuous everywhere on the closed interval from a to b because it's differentiable everywhere on that closed interval in order for the nth derivative to exist, and therefore it will be continuous everywhere because differentiability implies continuity. So the only one that actually we're not guaranteed is going to be continuous is the nth derivative, because we're not insisting that the n plus 1th derivative is going to exist everywhere on the closed interval from a to b. So that has to be then stated as a separate condition, which is why I've written this here. So we're assuming that all of these are continuous, including that nth derivative of f. The final additional condition we're going to need in order to be able to apply Taylor's theorem is we're actually going to need the nth derivative to be differentiable itself. So we're going to need the n plus 1th derivative to exist, but it doesn't need to exist everywhere on the closed interval from a to b. It only needs to exist everywhere on the open interval from a to b. So it doesn't necessarily have to be the case that the nth derivative is differentiable at the endpoints a and b. And that's why we still actually need this stated as a separate condition, that this one is continuous on that closed interval from a to b, because it being differentiable on the open interval isn't strong enough to then imply that it's continuous everywhere on this closed interval, because the endpoints are the problems. We can't be assured that it will be continuous on those endpoints without stating it as a separate condition. So overall, we need the function to be differentiable everywhere on the closed interval from a to b n times, and we need all of those derivatives to be continuous, and then we need it to be n plus 1 times differentiable, not quite on the closed interval, but on the open interval from a to b. This is the weakest condition that you need in order to be able to apply Taylor's theorem. If it is differentiable even more times, that's brilliant. You know, if it's infinitely differentiable and all of the derivatives are continuous, like polynomial functions are, for instance, that's absolutely wonderful. But this is the weakest condition that you need to be true in order for Taylor's theorem to hold true. So again, it could be the case that it's differentiable n plus 1 times on the closed interval from a to b. That's wonderful also, but that's not the weakest condition. I'm stating the absolute weakest condition that you need. If these conditions are not met, you cannot apply Taylor's theorem. If more stronger conditions than these are met, then that's fine. You can still apply Taylor's theorem. These are the weakest conditions you need. Taylor's theorem then says, consider the nth Taylor polynomial, which we will call t subscript n, and it's going to be a function, so it's going to be defined on this closed interval from a to b, and we're going to centre this polynomial around the left endpoint of the interval a. Now, this is something we're going to do throughout the video. We're going to centre the Taylor polynomial around the left point of the interval, and we're going to be talking about approximating the function at the right point of the interval. However, the whole theorem works in the mirror image case as well. You could centre the Taylor polynomial around b and use it to approximate the left boundary of the interval a. However, I feel it's more natural to work in the positive direction rather than going in the negative direction. So we will be doing that throughout the video. However, be aware that the whole thing works in the mirror image also. I'll say more about this later on, don't worry, if you're not completely understanding what I'm talking about at this stage. The whole argument that we're going to use to prove this works in the mirror image as well. We're just going to focus on the more natural way, which is the positive direction. So we're going to build a Taylor polynomial then that's going to be based around the point A, and it's going to map every point inside this interval onto a value. So x is the variable, x is some point inside this interval, and the value it will map it onto is given by the following, and hopefully you're familiar with this expression from calculus. So it's the value of the function at a, which is a constant, plus the value of the derivative of the function at a times x minus a. And of course, all of these derivatives are going to exist by our conditions here, plus onwards, the second derivative of the function evaluated at a times x minus a squared over 2 factorial, and of course it goes on and on all the way up to the nth term, that will be the nth derivative of the function evaluated at a times x minus a to the power of n over n factorial. And we can write this in a more compact form. So we can write this as the sum from r is equal to 0 to n of the half derivative of a times x minus a to the power of r over r factorial. Now, I'm not giving a huge amount of motivation into why this is defined like this, because I'm assuming you're all familiar with this from calculus. So we will denote this simply by this a lot of the time, because of course this is extremely complicated and this doesn't look particularly pretty either. Just to convince you that this is indeed equal to this, when r is equal to 0, this gives this term. When r is equal to 1, this gives this term. R is equal to 2, it gives this term, etc. all the way up to the nth term, which gives this one here. So Taylor's theorem then is all about this Taylor polynomial centered at a and using this to approximate the value of the function now at the other end point, b. So we can consider, I don't know why I'm writing capital, let me get rid of that. So consider f at b, and I want to approximate this with the Taylor polynomial evaluated at b. Now, if we just draw a picture to illustrate this, so we have our axes, here is our interval AB, and here might be our actual function, f, and then I'll draw in green, this might be the Taylor polynomial, t. And of course, the value of the Taylor polynomial will agree with the value of the function at a itself, because if you plug a in for x here, all of these bits vanish because you've got a minus a, a minus a, a minus a. So all of this vanishes and you've just got f of a. So the value of the Taylor polynomial a is the value of the function at a. So they agree there, they're absolutely in agreement there. But then all the other points, they might not be in agreement unless it happens that this function is that exact polynomial. But in general, it won't be. So the Taylor polynomial isn't going to match f. And then we're thinking about this, the value at b, so using the Taylor polynomial to approximate the value of the function at b. So we're saying f of b can be approximated by the Taylor polynomial at b. Now, Taylor's theorem, which, by the way, is not an intuitive theorem at all. To me, this is not intuitive whatsoever, this result. But it says, the proof, however, is actually incredibly simple. It says that if you want to know how much the Taylor polynomial is wrong by, i.e. what this error is equal to here, what f of b minus the value of the Taylor polynomial at b is equal to, it is given by this. So we can rewrite this to make it an equality. F of b is equal to the value of the Taylor polynomial evaluated at b plus this correction term, this error term, which is f differentiated n plus 1 times evaluated at some magic value xi times b minus a to the n plus 1 over n plus 1 factorial. Let me explain this. So this bit here, this is kind of like the next term along in the Taylor polynomial. If you think about having another term here, it would be the n plus 1th derivative evaluated at a times x minus a to the n plus 1 over n plus 1 factorial. If you then evaluated that at b, you'd be plugging in b here and you'd get b minus a to the power of n plus 1 over n plus 1 factorial. Of course, you wouldn't get f differentiated n plus 1 times evaluated at xi. You'd have a here, but we'll come back to that. So that's where this bit comes from. What does this bit then mean? Xi is some value inside the interval AB. So it's somewhere on this picture. So what this theorem is saying is that there will exist some xi, some magic number inside this interval AB, in between AB, such that if you ask what the derivative of the function at what the n plus 1th derivative of the function is at that xi, and you plug it in here, multiply it by this difference between b and a, this length here, to the power of n plus 1, and then divide it by n plus 1 factorial, somehow magically that equals this error value. That there exists some xi for which this works inside that interval AB, that is what Taylor's theorem is. As I was saying earlier, the theorem works the other way round as well, so it doesn't necessarily need to be the case that the point that we're basing the Taylor polynomial around is on the left and the point that we're approximating is on the right. Instead, we could have based the Taylor polynomial around B and used it to approximate A. This theorem would still hold true, that there would be a magic xi in between A and B, such that it plugged in to this formula here, and you'd have to swap B and A around here because they're now taking the opposite roles. You'd have to have A minus B rather than B minus A. But there will still exist a xi in between the two, such that this magic formula now makes that error value between the value of the function at A and the Taylor polynomial at A. So we're not going to focus on that case in this video. We're going to focus on the case as we've set it up thus far, where A is the point that we are basing the Taylor polynomial around and B is the point that we're approximating. However, the whole proof argument that we're going to go through for this way round works exactly the same way for the mirror image case. So let's commence the proof of this then for this way round, where the point which we're basing the Taylor polynomial around is on the left and the point that we're approximating is on the right. So let me begin by showing you something simpler. Let me begin by showing you that there is some value, some real number here, which we'll call C, that makes this work. So f of b is a number. It's the value of the function at b. Tnb is also a number. It's just the value of the Taylor polynomial at b. So we can subtract Tnb away from f of b, just subtract Tnb from both sides, and we'll get that this is equal to c times b minus a to the power of n plus 1 over n plus 1 factorial. Now, these are numbers as well. N, yes, is a general natural number, and this theorem is going to apply for all n's, but in a specific problem where you've chosen your n is just a constant. B minus a is also just a constant. That's that difference between these two numbers, the length of your interval. So n plus 1 factorial is just a number. This is also just a number. So we can multiply through by n plus 1 factorial and divide through by this, because this isn't going to equal 0 as long as this interval isn't, as long as this interval isn't just a single point, which we're assuming it isn't, then this is not going to be 0. So we can then rearrange this to get that c is equal to n plus 1 factorial over b minus a to the power of n plus 1 times f of b minus tn at b. So what I have shown you here is this is going to be some real number, so there is a value c that if you put it in here, it gives you the right error that is needed to make this equality work. What Taylor's theorem then boils down to is I need to show you that there is some xi inside this interval ab such that the n plus 1th derivative of the function evaluated at that xi is equal to this magic c value that makes all this equality work. So this is how I'm going to do this. I'm going to define a new function on my closed interval from a to b, and it's going to be defined by this function rule as follows. I'm just going to actually move the page so I've got more space. So we're going to have the function f. We're then going to subtract off the Taylor polynomial evaluated at x, and we're also going to subtract off this magic c value times x minus a to the power of n plus 1 over n plus 1 factorial. So let me convince you that this is going to be a function on that closed interval from a to b. So the function f is already defined on the interval from a to b. the Taylor polynomial is also going to be defined on that interval a to b. It's a nice polynomial function given by this. You take any x inside here, plug it in here, and it will give you a value. That's the value of that Taylor polynomial at x. So our function, we're taking f of x, we're subtracting the Taylor polynomial at x, and then we've got this term as well, which we got from this new magic value c, which I've shown you exists. I don't know necessarily what that c is equal to, but it does exist, it is some real number. And I remember I'm trying to show that this c is going to equal the n plus 1th derivative of f for some xi, some magic xi in that interval a, b, and this is how I'm going to go about it, by studying this function. So we've got our c there, and then it's to the power of x minus a, sorry, it's times x minus a to the power of n plus 1 divided by n plus 1 factorial. So this is just a polynomial term, x minus a to the power of n, that's just a polynomial, and then it's divided through by n plus 1 factorial, which is just a constant, so it's still just a polynomial function. So I've just got f minus 2 polynomial functions here. I apologise for all these seagull noises. I can't do anything about them, I'm afraid. I hope they're not too distracting. So I hope you agree that this function that I've created here is going to be defined everywhere on my closed interval AB. I want to convince you of some other things. I want to convince you that all of these initial criteria that applied for f are still going to apply for my new function. So remember, we have that the function f is n times differentiable on the closed interval from a to b, and all of those derivatives are going to be continuous everywhere on the closed interval from a to b. Also, that the function f is going to be n plus 1 times differentiable on the open interval from a to b. So fn itself is differentiable everywhere on the open interval from a to b. Those were the criteria that I needed. Now, I claim that these are still going to apply for this, and the reason is that these things are just polynomial functions. We're just adding on the additive inverse of a nice polynomial function and another nice polynomial function here. Polynomial functions are infinitely differentiable. Their derivatives are all going to be continuous, and that actually applies for the entire real line. So certainly on our closed interval from a to b, these polynomial functions, minus tnx and minus c times x minus a to the power of n plus 1 over n plus 1 factorial, these are going to be infinitely differentiable. All the derivatives are continuous. Therefore, we are just taking this function and adding it effectively to another function that is guaranteed to obey all of those criteria. In fact, of course, this thing that we're adding on, this obeys far more than these criteria. However, it's certainly going to be true that for those polynomial functions, they are going to be n times differentiable on the closed interval from a to b, and all their derivatives are going to be continuous, and they're then going to be n plus 1 times differentiable on the open interval from a to b. So then, because of the fact that if you add two differentiable functions together, you get another differentiable function, you can conclude that overall this thing is going to be n times differentiable on this closed interval from a to b. All of those derivative functions are going to be continuous on that interval, and it's going to be n plus 1 times differentiable on the open interval from a to b. So I hope you agree with me with that. So this is when this starts to get beautiful. So let's write out this Taylor polynomial now in full, because it's going to help us understand what happens here. So our function then is going to be f of x minus, and then we're going to have this full Taylor polynomial, which is f of a plus f prime at a times x minus a plus, and then it goes on all the way up to the nth term, fn evaluated at a times x minus a to the power of n over n factorial. And then we've also got minus this final term, this Taylor term at the end, c times x minus a to the power of n plus 1 over n plus 1 factorial. Now, let me just put some brackets there. Let's think about drawing a picture of my function here. So if I do this, it's going to be defined on this closed interval from a to b, Now let's think about what its values are going to be at the two endpoints, a and b. If you put in a here, we've got f evaluated at a minus the Taylor polynomial at a, which we know is the same thing as f at a, so that's overall 0, minus this thing evaluated at a minus a goes to 0, so this doesn't do anything. So overall it's going to be 0 at a. So I might actually plot this in a different colour, so in red here, that's its value at a. And then what's its value at b? So we have f evaluated at b minus the Taylor polynomial evaluated at b minus this magic Taylor term. Now let's think about what this is going to do. If you put in b here, this goes to b minus a to the power of n plus 1 over n plus 1 factorial. But remember what c was defined to be. It is equal to the c that satisfies this equation. So it means that if you put in b into here, that's going to be equal to this bit here, which is equal to f of b minus tnb. So it's equal to this first bit here. And we're subtracting that off. So, imagine taking this to this side here and having minus c times b minus a to the n plus 1 over n plus 1 factorial. It'll overall equal 0. And that's exactly what we get here when we stick in b. We'll have f of b minus tnb, that's this bit, minus this bit, which is therefore overall going to equal 0. So also at x is equal to b, the function is going to be equal to 0. Now what we're going to do is apply Rolle's theorem to our function. So Rolle's theorem, remember, says that if you have a function that's defined on a closed interval from a to b, and the value of the function at the two endpoints is equal to one another, which in this case it is, they're both equal to 0, and you know that the function is continuous everywhere over the entire closed interval and it's differentiable everywhere over the open interval, then you can conclude that somewhere inside the interval, so on the open interval AB, the first derivative is equal to 0. Now, this function satisfies all of those criteria for Rolle's theorem. It is, remember, going to be n times differentiable on the closed interval from a to b, and all of its derivatives are going to be continuous, and then it's n plus 1 times differentiable on the open interval from a to b. So that certainly means that it's going to be continuous on the closed interval from a to b and differentiable once on the open interval from a to b. In fact, it's far more than that, but it certainly satisfies the criteria for Rolle's theorem. So we can conclude, therefore, that somewhere inside this interval, in between a, b, there's going to be a point where the derivative of this is equal to 0. So I'm going to call this point, it might be there, I'm going to call this point xi, but it's not our final xi, so I'm going to call it xi0. In fact, I'm not going to call it xi0, I'm going to call it xi1, because it's a first derivative, it's the point where the first derivative is going to equal 0. So there's going to exist some point xi1 such that the first derivative is equal to 0. Let's actually differentiate our function now. So this is our function written out in full. Let's differentiate it. It differentiated is going to become the function differentiated, and then our Taylor polynomial differentiated once. This bit's going to vanish, of course, and then we know how to differentiate these polynomial terms. So we're going to end up with minus f prime evaluated at a, and then we'll have the second term will be f, the second derivative of f evaluated at a, times x minus a, and now it'll just be over 1 factorial because when we differentiated this squared term, the 2 has come down and cancelled with that 2 there. And then we'll go all the way up to, it'll still be the nth derivative evaluated at a, but now it'll be to the power of x minus a to the power of n minus 1. And instead of being over n factorial, it'll be over n minus 1 factorial, like so. And then finally our Taylor correction term will have our c coefficient, and then we'll have now x minus a to the power of n over n factorial. So what we know is that there must exist some point xi1 such that if you stick it in here, the value is going to be 0. Now you might be expecting me to now stick this xi1 into here and do something with it. I'm not going to do that because I don't actually care about xi1. Xi1 is not going to be our final xi. We have got a lot more differentiation to do, a lot more applications of Rolle's theorem before we actually get our xi. What I am instead going to note is that think about what the derivative of our function is at this point a over here. Well, stick a into here. We're going to get f prime at a. If we stick a in here, we're going to get f prime at a, and then all the rest of this is going to go to 0 because, again, you're sticking a into these x minus a powers here, and all of those are going to go to 0. So this is just going to become minus f prime of a. So overall, we've got 0 so far. And then here, this final term, if you stick a into there, again, it's just a power of x minus a, so it's going to go to 0 as well. So the value of the derivative of our function is 0 at a, and we also know that this point here, xi1, where the derivative of our function is 0. So what we're now going to do is apply Rolle's theorem again, this time not to our function, but to the derivative of our function, because the derivative of our function has the same value at a and xi, and it's also going to be continuous everywhere on that closed interval from a to xi, and differentiable everywhere on the open interval from a to xi. So we can then conclude that there's a point in between a and xi1 where its derivative in turn is equal to 0, i.e. the second derivative of our function is going to equal 0. So just to help us keep track of this, I'm going to write down up here all of the things we know about our function. So we know that it is going to be n times differentiable, so I'll abbreviate this to n differentiable, on this interval, and those derivatives are all going to be continuous over that closed interval. We then know that it's n plus 1 times differentiable on the open interval ab. Those are the criteria that we know about this function. Let's now just consider a little bit more detail how we can now apply Rolle's theorem here. So we know that the value of the first derivative of our function is going to be the same at a and xi1. We then also need to know that it's going to be continuous, the first derivative as a function on this interval from a to xi1. In order to be able to apply Rolle's theorem, we need to know that it's going to be continuous everywhere on that interval. Well, that's guaranteed by this up here. Remember, our function, this whole thing, is going to be n times differentiable, and the derivatives are all going to be continuous on this much bigger interval, the whole interval from a to b. So it's certainly going to be true that this subset of this interval, over that subset, it's going to be differentiable and the derivatives are going to be continuous. So the first derivative is guaranteed to be continuous over there. It also, to apply Rolle's theorem, needs to be differentiable on the open interval from a to xi1. That again is going to be true because it is going to be differentiable over again this entire closed interval, so it's certainly going to be differentiable on this subset. So yes, everything's fine. We can apply Rolle's theorem to this, and we can say that there is then going to exist some new point in between a and xi1, which we'll now call xi2 because it's the one where the second derivative is going to equal 0, where at this magic point the second derivative of our big function here is going to equal 0. Let's write this down then. So the second derivative we now want of our function, so we're going to differentiate this again. So doing that, I'll go back to the white pen. We'll now have the second derivative of the function evaluated at x. Differentiating the Taylor polynomial, we'll now no longer have that f prime at a, that's gone. So we'll have f2 at a, and it will now just be a constant term because this will have gone. And then we'll have plus f3 evaluated at a times now just x minus a to the power of 1. And it will be over 1 factorial because this has now been differentiated twice. Initially it will have had to the power of 3 up here over 3 factorial, but differentiating it twice, the 3 will have come down and cancelled with the 3 in the 3 factorial, and then the 2 will have come down and cancelled with the 2 in the factorial, so we'll just be left with 1 factorial, and then this will go all the way up to fn evaluated at a now times x minus a to the power of n minus 2 over n minus 2 factorial. And then finally we'll have our Taylor correction term, so minus c times x minus a to the power of n minus 1 over n minus 1 factorial. Now again, you might be expecting me to stick in xi2 here and do something with it. I'm not going to do that because I don't actually care about xi2. We're on our way towards xi and we need to just continue on. And hopefully, if you pause the video, you might be able to, in fact, you might not even need to pause the video, you might see what our next move is going to be. We're going to think now, what is the value of the second derivative of our function at a? So this is our second derivative. Stick in a here. It's going to all come out as 0 is the answer, and I'll show you that in just a moment. But the reason it's coming out as 0 is because of the way the Taylor polynomial works. The way, when you differentiate the Taylor polynomial however many times, its derivative is going to agree with the derivative of our initial function. So if we're subtracting this from this, it's always going to come out as 0, and this term isn't going to affect it because until we get up to the n plus 1th derivative, it's always going to have this x minus a power appearing there, and therefore is going to vanish. So plugging in a here, we're going to get the second derivative evaluated at a minus, and then all of this just goes to the second derivative at a because all of these just cancel or give 0 when you substitute in a. So therefore this cancels with this to give 0, and this doesn't affect it at all at this stage because it's still got this power of x minus a in it, so it also goes to 0. And hopefully you can then see what we're going to do next. We've got the second derivative of the function is going to be 0 at a. It's also going to be 0 at this xi2, so we can now apply Rolle's theorem to the second derivative over this interval from a to xi2. And again, it's going to meet the criteria because of those criteria that we initially had for the function. So it's going to be continuous everywhere on this interval from a to xi2 because the second derivative is going to be continuous everywhere on the interval from a to b, so it's certainly going to be that on this subset. It's also going to be differentiable everywhere on the open interval because it's differentiable everywhere on the closed interval from a to b. So you're going to continue this argument on and on. You'll get a xi3 where the third derivative is equal to 0. You'll find that the third derivative of the function at a is also 0. You can then find a xi4 by Rolle's theorem, and where the fourth derivative is 0, you'll find the fourth derivative is also 0 at a. You continue on and on right up until you find a xn where the nth derivative of the function is going to be 0. So that's where we'll skip to now. So skipped quite a few steps and we're now at xn. And let's think about what the nth derivative of our function is going to be. So we'll go actually back to our original formula for our function here. So the nth derivative is going to be the nth derivative of the function f minus the nth derivative of the Taylor polynomial. Well, of course, once you've differentiated this n times, all of these bits will have gone. All you'll be left with is this bit. This differentiated n times, all of these powers will have gone now. In fact, differentiating something to the power of n times, you'll just be left with 1 at the end. And all those differentiations will have led to this n factorial cancelling as well. When the n came down, it will have cancelled with the n factorial. When the n minus 1 came down, it will have cancelled with the n minus 1 in the n factorial, etc. So it will have gone as well. So all you'll be left with actually here is the coefficient as a constant term, which is the nth derivative of f evaluated at a. That's all that's left of this great big Taylor polynomial once you've differentiated it n times. And then finally our correction term will still exist because differentiating this n times, you'll have a linear term by this point. So you'll have minus c times x minus a, and then it will be over 1 factorial because all the other parts of the factorial will have cancelled by this stage. So the bit that we've got to then is we know our function has been differentiated n times. This is the function for the nth derivative. We know that it is n times differentiable and that this derivative is going to be continuous everywhere on the closed interval from a to b. We also know that we have this psi n, which we got through this continued recursive process of using Rolle's theorem, where xi n is going to be somewhere in between a and b, and it's going to be a point where this nth derivative is equal to 0. Now we're going to apply Rolle's theorem one final time, because sticking a into this, a in here gives the nth derivative of f at a, it cancels with this. Stick in a here, it gives 0. So the value of the nth derivative of my function at a is 0. I also know that it's going to be 0 at xi n. So I'm now going to apply Rolle's theorem one final time over this interval from a to xi n. And this is going to give me my final magical xi that's going to be the one that makes Taylor's theorem work. How do we know we can apply Rolle's theorem? Well, it needs to be continuous everywhere over this interval. Well, I know that the nth derivative of this function is continuous over the entire closed interval from a to b, so it's certainly going to be continuous in a subset of that, which is the interval from a to xi n. I also need to know that it's differentiable everywhere on the open interval from a to xi n, and this is where I actually am now finally going to use this condition. This is why this is the weakest condition that you needed in order to be able to apply Rolle's theorem. We know that this function is n plus 1 times differentiable on the open interval from a to b. This is a subset of that open interval from a to b. The n plus 1th derivative of this function is going to be the derivative of this nth derivative of the function. So this is indeed going to be differentiable everywhere on that open interval from a to xi n. That's why that was the weakest condition, that the n plus 1th differentiability only needs to apply to the open interval, because it's this final condition that you need for the final application of Rolle's theorem. So now, by Rolle's theorem, there's going to exist a point in between a and xi n where the derivative of my nth derivative is equal to 0, i.e. where my n plus 1th derivative is equal to 0, and this is now that magic point xi. So let's differentiate this one more time. So we'll get the n plus 1th derivative of f evaluated at x. This is a constant term, so this is a linear term, so we then end up with this is just equal to c. And now we finally stick in xi to that. So we know that there must exist a xi in between a and xi n such that this is equal to 0. So that means that when you evaluate this n plus 1th derivative at xi, it must be equal to 0, i.e. that c will equal this n plus 1th derivative at xi. And that has then proven that for this xi, this magical xi that I found through this repeated application of Rolle's theorem, the n plus 1th derivative of the function f evaluated at that xi is going to equal that magic number c that makes the Taylor remainder term work. So I think to finish, we will summarize what we've done, or try to summarize what we've done. So we'll go back to the top. So you have some function defined on the closed interval from a to b that is a real valued function. Taylor's theorem holds true for a general natural number little n. For a given little n, in order to be able to apply Taylor's theorem, these are the conditions that you need to be true. You need your function to be n times differentiable everywhere on the closed interval from a to b, and all of those n derivatives need to be continuous everywhere on the closed interval from a to b. And remember, at the beginning we discussed that for all of the ones apart from the nth one, it's immediately obvious that they're going to be continuous because of the fact that they're differentiable. But for that nth one, that is an important additional condition that you've got there. So that's why it's stated. And then finally, the function needs to be n plus 1 times differentiable, not on the closed interval, but on the open interval. If you have it on the closed interval, fantastic, but that's not the weakest conditions, the weakest criteria you need in order for our proof to hold. So remember, our proof consisted of doing Rolle's theorem, applying Rolle's theorem n plus 1 times, and this final bit here was the weakest condition you need in order to be able to apply Rolle's theorem that final n plus 1th time. So let's now look at the statement of Taylor's theorem once again. So it says if you have the Taylor polynomial based around the point A here, and you want to use it to approximate the value of the function at B, then the error term, the difference between the two, is given by something of this form. There will exist a xi in between A and B such that if you plug it in here, this works, this equality is true, i.e. in full, there exists a xi such that the n plus 1th derivative of the function at xi times b minus a to the power of n plus 1 over n plus 1 factorial is equal to the difference between the two, i.e. f of b minus the Taylor polynomial evaluated at b. Not an immediately obvious theorem at all, but one that we've seen doesn't have too complicated a proof. And as we've said previously, this holds true the other way round. We could have had the Taylor polynomial based around b and then been using it to approximate a. It would still hold true, you just need to swap b and a around here, and obviously you'd have to put in a here instead of b. But the theorem still holds true. Xi is going to be in between the 2 points, so in between a and b, and there will exist a xi such that Taylor's theorem holds true. We looked at the proof for a being the point that you centre the polynomial around and b being the point that you are approximating, but the proof is exactly the same in the mirror image direction. You repeatedly use Rolle's theorem just the same as we did here. So going over the proof again, we firstly noted that there is some real number such that if you multiply it by b minus a to the power of n plus 1 divided by n plus 1 factorial, it is equal to this difference between the value of the function at b and the Taylor polynomial at b, because quite simply you can rearrange this algebraically like so. So there will exist a real number such that this is true. And we then considered this function f of x minus the Taylor polynomial, the nth Taylor polynomial centred at a, minus this magic number c times x minus a to the power of n plus 1 over n plus 1 factorial. We discussed how, because f is n times differentiable on the closed interval from a to b, all its derivatives are continuous, and then it's n plus 1 times differentiable on the open interval, and because these are just polynomials which are infinitely differentiable, all their derivatives are continuous over the entire real line, then when you add them together, it will certainly still be true that the overall thing will be n times differentiable on the closed interval from a to b. All of its derivatives will be continuous, and it will be n plus 1 times differentiable on the open interval from a to b. We then did this incredible procedure of doing Rolle's theorem over and over again until we got to this xi n, where the nth derivative of this function is guaranteed to equal 0. So just going over this in a bit more detail, we noted that the value of this function at a and b is going to equal 0, i.e. the same thing. It's also going to be continuous everywhere over the entire interval and differentiable everywhere over the open interval. So we can then apply Rolle's theorem to say that somewhere inside that interval there will be a point where its derivative is equal to 0. We called that xi1. We then differentiated this function, the answer is over here, and noted, oh look, the derivative is also 0 at a. So if we now consider the first derivative defined on this interval from a to xi1, we can then apply Rolle's theorem again, and these criteria up here allow us to do this. We do this over and over again because there's now a point xi2 where the second derivative is guaranteed to be 0. We also look at the second derivative at a and find that it's 0, so we can then apply Rolle's theorem to find a xi3, and we go on and on all the way to xn, where the nth derivative of our function is guaranteed to be equal to 0. And we also note that the nth derivative of the function a is going to equal 0. So we can then apply Rolle's theorem one final time, find a number in between, which then is the magic xi, where the n plus 1th derivative of our function is guaranteed to be 0. But then look at what the n plus 1th derivative of our function is equal to. It's just equal to this thing over the entire interval from a to b, but certainly over the interval from a to xn. So you then plug in this magic value xi, which is guaranteed to exist, and it must be the case that this is equal to 0. Just rearranging that, it therefore implies that the n plus 1th derivative of the original function f, from which our more complicated function was constructed, will equal this magic value c. And we have therefore proven that there is some xi inside that interval from a to b, such that the n plus 1th derivative of xi is equal to that perfect value c that fitted in here makes this true, and therefore we are given Taylor's theorem. So we'll end there. Thank you for watching.